When can we say the work is done maximum? So it is nothing but when the angle between the force and displacement is 0, then we can say the work done is maximum. When the force and displacement are perpendicular to each other, the angle between them will be 90 degree. When the value of theta is 90 degree, the work done will become 0. The energy that possessed by a body by the virtue of its motion or position or configuration, we will term it as mechanical energy. Hello everyone. Welcome to session 1 of chapter 6, Work, Energy and Power. This is Swati from Department of Physics, Vidhyaashram University College, the Temple of Excellence, Mysuru. Dear children, in this chapter, as the title says, we are going to study the various phenomena and the concepts that involve with work, energy and power. So let us start with a basic introduction. So in understanding the chapter work, energy and power, it is very important to understand the operation on scalars. We all know what are scalars. It is nothing but the physical quantity which has only magnitude. So how to define the scalar product of two vectors? What is a vector? Vector is nothing but any quantity, a physical quantity which has both the magnitude and direction. We will call it as vector. So here, let us now know about the basic definition of scalar product of two vectors. It is also called as the dot product. So how to define this dot product? So product of two vectors can be calculated as dot product as well as cross product. So to define the scalar product of two vectors or dot product, let us consider two vectors, that is vector A and vector B. So the scalar product of these two vectors can be calculated by taking the product of magnitude of two vectors. So this modulus represents the magnitude. So we are taking the product of magnitude of two vectors and the cosine of the angle between these two vectors. The theta is the angle between two vectors A and B. So it is defined as the product of magnitude of two vectors and cosine of the angle between them. So this is how we have to define the scalar product of two vectors. So in the upcoming concepts, we need this idea of dot product between two vectors, and hence I am giving you an idea in the beginning itself. So let us begin with the study of work. So as the name suggests, in this chapter, we are going to study about the work, energy as well as power. So what is work? How to define work? How the work can be done? When can we say that the work is done? So let us understand that by knowing the definition first. So work is defined as the product of displacement and the component of applied force in the direction of displacement. So work is defined as the product of force and displacement. So here the displacement will take place in the direction of applied force, or the force is applied in the direction of displacement that takes place. Generally, the work is defined as the product of force into displacement. Here force is also a vector, displacement is also a vector. So now let us write the scalar product of these two vectors, that is a dot product, that is nothing but W is equal to, according to this equation, it is F into X cos theta. So Fx cos theta is nothing but the scalar product between these two vectors. So I hope the definition of work is clear to everybody. So the definition says the product of displacement and the component of applied force. Here X is displacement, F is applied force, and this force in the direction of displacement. Whenever we apply a force, the displacement or the change in position takes place in the direction of applied force. That is what the definition is saying. So the expression for work is W is equal to Fx cos theta. Here to explain the terms, we must know what are the terms, where F is nothing but the force acting on the body, X is nothing but the displacement of the body, and theta is the angle between the directions of force and displacement. Now this is the general form. Let us study some various special cases. So what are the special cases? If the angle between F and X, that is theta, is equal to 0, so then what happens? So cos 0. So cos 0 value is 1. So what happens if this value is 1? W is equal to F into X we will get. So this is the maximum work done. When can we say the work is done maximum? So it is nothing but when the angle between the force and displacement is 0, then we can say the work done is maximum. Suppose if the theta is 90 degree, that is the angle between force and displacement is 90. So what is the value of cos 90? Cos 90 is 0. So this entire term will become 0 and the work done value we will get as 0, that is the minimum work done. So whenever there is a 90 degree angle between force and displacement, then we can say that the work done is minimum. So as we have discussed, work done, we came to know that it is nothing but the dot product of F1 x, and hence we can write it as Fx cos theta. So what is this nature of work? So this work done can be a 0 or it can be positive or it can be negative. So we can make out what is a positive work done, negative work done, but we must know what is 0 work done. So 0 work is nothing but by considering a relation W is equal to Fs cos theta, we can derive or we can understand what is a 0 work. If theta is equal to 90 degree, as I told, the angle between the force and displacement is 90 degree, then we will get cos 90 value is 0, so this entire term will become 0 and hence the work done will be 0. So work done is 0 when the force and displacement are perpendicular to each other. When the force and displacement are perpendicular to each other, the angle between them will be 90 degree. When the value of theta is 90 degree, the work done will become 0. So and hence we will call it as 0 work done. So now we came to know about what is work done. What are the nature of work done? Let us now write the SI unit of work done. So the SI unit of work done is joule and symbolically it is represented by the letter J. So remember the SI unit of work done is joule, symbolically it is represented as capital J. How to define this joule now? Or you may also get the question, define the SI unit of work. SI unit of work is joule. You can directly get the question as define joule or define the SI unit of work. So to answer this question, define the SI unit of work, we must know what is the SI unit of work. So the unit is joule. Let us define 1 joule. How to define 1 joule? Consider this equation, W is equal to Fx cos theta. Now see here, if the work is said to be 1 joule, the remaining terms whatever we have in the RHS must be always 1. So to define 1 joule, we have to consider the force of 1 Newton and the displacement will be 1 meter and this cos theta value we have. So theta value must be 0 degree. So because cos 0 is equal to 1. So then we will get the value W as 1 Newton meter or 1 joule. So the work is said to be 1 joule when a force of 1 Newton displaces a body through 1 meter in the direction of force. When 1 Newton force is applied to displace a body of 1 meter, then we can say that the work is done. Then we can say that the work done is 1 joule. So now we have to understand the work done by a constant force. So to understand this, we have to consider a graphical representation. So the graphical representation of work done by constant force is also called as force and displacement curve. So we have taken force along y-axis and displacement along x-axis and hence it is called as force displacement curve. So understand the graphical representation before writing an expression for work done by a constant force. Here you can observe if the displacement increases also, the force remains constant. So here we are understanding what is the work done by constant force, because work done by can be calculated by considering the product of force and displacement. So displacement is happening over there but the force is remaining constant, and for this what is the work done, we are now going to write the expression. So the above graph shows the force F constant with the increasing in displacement. You can observe here the displacement is increasing but the force remains constant. So the work done by the force can be calculated by considering the area under force displacement curve. So by considering the area under this curve, we can find the total work done. So how to consider now the area of given curve, that is OA into OC, because that can be calculated as the length into breadth, and here OA represents force and OC represents displacement. So OA into OC gives us the area under this curve, and OA is replaced by F and OC is replaced by X. So W is equal to force into displacement. Whenever we have a constant force, the work can be calculated by the expression F into X. Similarly, we can even calculate this for a variable force. So let us now understand the work done by a variable force. So to understand this, we must look into the graph properly. So here we can see that the force from P to Q is not constant. It is varying. So here we can understand, we are going to analyze what is the work done by a variable force. So the figure shows the variation of force acting on a body with its position. Here you can observe the force is taken along y-axis and the position is taken along x-axis. So this figure is clearly saying that the force acts on a body with respect to its position. So in this case, the force is not constant from P to Q. You can see here, there is a variable force that acts from P to Q. The force is not constant. So therefore, the region below the curve PQ is divided into number of rectangles. Here we can see that we can observe the area is divided into the number of small rectangles like ABCD, each of width dx. ABCD is a rectangle, each rectangle of width dx, and which is extremely very small. So through the displacement of dx, force is constant. So with the displacement of dx, the force is constant, but the force is not constant from P to Q. So now we have considered each rectangle with the width dx. So the work done during displacement dx is given by dw. dw is nothing but the small work done. Since we are studying only about the rectangle, which is the small component of the area, so we can write work done is equal to dw, which is nothing but area under the curve AB. So you can see here, this is the smallest rectangle we have considered of width dx. So the work done at this part can be calculated by taking the area under the curve AB. So how to find the area of rectangle, that is length into breadth. So here we can say that AC into CD, that gives us length into breadth. So it is AC into CD. So here you can observe AC is nothing but the force which is varying along y-axis, and CD is nothing but the position. So we can write F into dx. So it is force into displacement. The total work done from initial position x1 to the final position x2. How to find the total work done from the initial position x1 to the final position x2? By integrating all the small work done. That is nothing but the sum of areas of rectangles. Integration is nothing but taking the sum. So to find the sum of all the rectangles, small rectangles, we need to integrate the equation, that is to find the total work done from the initial position x1 to the final position x2. So by integrating small work done from initial position x1 to final position x2, we are bringing all the small work done together, we are finding the sum, which means we are integrating to find the total work done. So here f and x are the continuous variables. So w is equal to x1 to x2. In the place of dw, we need to substitute the force and displacement terms, that is f into dx. So here f is the function of x. So this is how we have to find out the total work done by a variable force. So by knowing the initial and final positions, we can find the total work done by a variable force. So this is what about work we have studied till now. So let us now understand certain terms which are related to energy. We all know what is energy. We are studying about energy since our lower standards. So what is energy? It is generally defined as the capacity to do any work. So to do any work, we need energy. So that capacity to do the work is called as energy. So what is mechanical energy? We know what is energy. So let us understand the term called mechanical energy. It is the energy possessed by the body by virtue of its motion or position or configuration. We will call it as mechanical energy. So the energy that possessed by a body by the virtue of its motion or position or configuration, we will term it as mechanical energy. So what are the types of mechanical energy? First one is kinetic energy and potential energy. So these two terms are the words which are very much familiar to all of us. We have heard these terms n number of times in our daily life. So what is kinetic energy? What is potential energy? What are the different examples that we can understand to know better about kinetic energy and potential energy? Let us now have a look. So what is kinetic energy? It is the energy that possessed by a body by virtue of its motion. So when the body is in motion, when the object is in motion, the energy associated with the object or a body is called kinetic energy. So we are now going to derive the relation between work and energy, and we will call it as work energy theorem. So the work done by the net force in displacing a body is equal to the change in kinetic energy of a body. So the work done by the net force, that is total force in displacing a body, is equal to change in kinetic energy. So far we have learnt what is work. Now we came to know what is mechanical energy, what are its types, and what is kinetic energy. So this work energy theorem gives us the relation between the net force that applies on a body, and that will be equal to the change in kinetic energy. So how it is related? Let us now derive an expression. So here there is a body which is having an initial velocity u, and the force is applied in this direction. So when the force is applied, the body is displaced. It is moving with the velocity v, final velocity. So this x is called as displacement. So in the given figure, u is the initial velocity of the body before we apply the force, and v is the final velocity of the body after the force is applied, and x is the displacement of the body. What is displacement? The change in the position. It is changing its position from one point to another point, and we will name it as x. So it is the displacement of the body. So let us consider the body is having a mass m and it is having a uniform acceleration a. So if the body is in motion, we know about the equation of motion that we have already derived in the previous chapter. So that is v square is equal to u square plus 2ax, or we can write this expression as v square minus u square, which is equal to 2ax. So let us now multiply both sides of this above equation by half into m. So what do we get by multiplying half into m to the above expression? So we get half m into v square minus u square, which is equal to half m into 2ax. Now what is the further simplification? Can we cancel anything? We can cancel 2 and 2 here, and here half m is multiplied with v square and half m is multiplied with u square, and that gives us half mv square minus half mu square, which is equal to m into a into x. But what is this m into a? That is mass into acceleration, which is nothing but force. So here we have half mv square, which means the final kinetic energy, minus half mu square, that is initial kinetic energy, which is equal to ma is nothing but force into displacement. So what is force into displacement? That is nothing but the work done. So we can write final kinetic energy minus initial kinetic energy, which is equal to F into x, because force is equal to mass into acceleration. So this final minus initial kinetic energy is nothing but change in kinetic energy, which is equal to force into displacement is nothing but the work done. Because we know Fx is equal to work done, so we can say that the total work done is equal to change in kinetic energy, and this is called as work energy theorem. So far we have discussed about the kinetic energy, how it is related with the work done. So let us now understand what is potential energy. It is nothing but the energy possessed by the body by virtue of its position or configuration. So this potential energy is again classified as gravitational potential energy, elastic potential energy, and electrostatic potential energy. As the name only suggests, it is very easy to understand about all these things, since if we have some basic idea about the names. So here, first one we have is gravitational potential energy. It is nothing but the energy possessed by the body by virtue of its position above the Earth's surface. So the energy possessed by the body by the virtue of its position. Why we are taking about the position? Because we are talking about potential energy. So above the Earth's surface, then we will call it as gravitational potential energy. For example, if you place a stone on the roof of the house, it will be at the rest position because it will be in a state of rest. It will be in its position, and that possesses potential energy. It will not be in a motion to have kinetic energy. So if we place one stone on the roof of the house, with respect to ground we are talking about, and hence there is a gravitational force between the stone and the ground, but the stone is at rest position, and we can give that as an example for gravitational potential energy. And the water stored on a overhead tank possesses potential energy. The water stored on an overhead tank possesses potential energy. The flowing water possesses kinetic energy. So these are the two examples, better examples to understand gravitational potential energy. So let us now write an expression for gravitational potential energy. It is nothing but mgh. So what is mgh? M is nothing but the mass of the body, g is nothing but the acceleration due to gravity, h is nothing but the height of the body from the surface of the earth. So from the reference point, this is the earth. Suppose if the object is placed on something, so this is the reference point. So this is the height of the body from the surface of the earth. So we will consider that to find the potential energy, and the expression is given by mgh. So our next topic is conservative force and non-conservative force. So what is the meaning of conservative force? When can we say that the force is conservative? So it is said to be conservative if the work done by the force depends on initial and final position of the body. So if the body's initial and final positions are taken into consideration, so it clearly says that a force is said to be conservative when the work done by the force depends on the initial and final positions of the body. For example, we can say that the gravitational force and electrostatic force and the spring force. So in these three forces, we will find out the work done by taking the initial and final positions into consideration. So non-conservative force is just converse to that, which means a force is said to be non-conservative if the work done by the force depends on the path followed between initial and final positions. It depends on the path followed, not only depends on the value of initial and final position, but it depends on the path that is followed between initial and final positions of the body. We will say it as non-conservative force. For example, the frictional force, air resistance and viscous force. So in all these three common examples, we can observe that the work done can be calculated by considering the path followed between initial and final position, and we'll name it as a non-conservative force. So it is very important to know about the difference between these two, which will be asked for 3 marks. So let us now write the differences between the conservative and non-conservative force. So conservative force is nothing but the work done by the force depends on only initial and final position of the body, but in case of non-conservative force, the work done depends on the path followed by the body. So the path between the initial and final positions, when the work done depends on the path followed by the body, we'll say it as non-conservative force. So work done in a round trip is 0. In case of conservative force, it depends on only initial and final position. It doesn't depend on the path followed, and hence in a round trip, the work done is said to be 0. So the work done in a round trip is not 0 in case of conservative force, because it doesn't only depends on initial position and final position, it also depends on the path followed, and hence it is not 0. And the work done is completely recoverable. We can recover the complete work done, because the reason is we will find the work done, and the work done here is dependent only on the initial and final position, and here it cannot be recoverable because here the work done is based on the path followed, and it is central in nature, and non-conservative force is non-central but it is retarding in nature. So these are the basic differences between conservative and non-conservative forces. So a very important question, examination point of view also. So this is about the basic introduction of work and energy and various terms involved with work and energy. So in this session, we have defined what is a work energy theorem, and we even derived an expression for work energy theorem, which is very important. And also we came to know about the conservative and non-conservative forces, the differences between these two, which is again a very important question, examination point of view. In the upcoming session, let us know more about these concepts. Until then, keep learning. Thank you.